Alright, so let's get started. Today we're going to look at another aspect of magnetic fields, an extremely interesting aspect. And I would like to introduce to you one of the Maxwell's equations. It's called the Ampere's law. So far, in our discussions of magnetic fields, may I start? Students, can oversee. So far, what we've seen are two basic facts. We've seen that moving charges produce magnetic fields. Okay? And the magnetic field is given by the Biot-Savart law. The magnetic field, due to a small element, mu0 over 4 pi, a moving charge with velocity qv crossed with the position vector r of the observation point from the location of the charge divided by r squared. So this is the Biot-Savart law, which tells us that a moving charge produces a magnetic field, and it's an empirical observation and is followed in most cases. And another version of this equation is that if we have a current carrying conductor, we splice that current carrying conductor into small segments, each of length dl, and take the cross product with the position vector and divide by the square of the distance. This also gives us the magnetic field produced by a magnetic charge. So now we know that moving charges are sources of magnetic fields. Static charges are sources of electric fields. Okay? And then we'll build the connection later when we study relativity. The other thing that we've learned is that if we have a moving charge inside a magnetic field, it experiences a force. And the force experienced is simply given by q v crossed with v. So you take the cross product of the velocity vector of the charge with the magnetic field at the location of the particle, you get the force on the particle. A current carrying conductor will also experience a force if it sees a magnetic field. So another version of this Lorentz relationship is dF, the force on a small segment, is given by I dl crossed with V. So these are the two of the four premises that we've learned. Remember, I told you that we're going to discuss four premises. Moving charges produce magnetic fields. They are sources of magnetic fields. And moving charges inside magnetic fields that have been produced from some other source experience a force. ये दो premises हम तफसील के साथ देख चुके हैं. Now I would like to come up with another point of discussion. It's a really important point of discussion, and I would like to start off by reminding you that if we have a current carrying conductor, okay, and this conductor is really long, and it carries some current I, and it's a steady current. Steady state has been achieved, there are no transients. And if I take a point P that is close to the conductor, this conductor is really long, I know that there is going to be a field at point P. What direction is the field at point P going to be? Into the plane of the blackboard. Okay, so I point my thumb in the direction of the current, so my fingers curl in here. So here the magnetic field is into the plane, here the magnetic field is out of the plane. So if I'm at a certain distance, D or R, from the current carrying conductor, I know that the field is going to be the same at all R's. So the field, in other words, is going to be cylindrically symmetric. So if I am at the same distance from this current carrying conductor, the field is going to be the same. Okay, and this field is going to point inward here. The magnitude of this field we've already derived is given by mu naught into I over 2 pi r. Okay, this is something we've derived, provided that this conductor is really long, or if the conductor is not long, this point is close to the conductor. I can draw the same figure in another way. I have this current carrying conductor, and current is flowing through this conductor. This is the direction of J, which is also the direction of the current. The magnetic field around this current carrying conductor is going to be circular. So I point my thumb in the direction of the current. The field is going to come out of the plane of the blackboard from the top and go inside at the bottom. So it's going to look like this. Okay, so the field is curled around the current carrying conductor. Okay, so I just hold in my hand the current carrying conductor with my thumb pointing in the direction of the current. My fingers are curled in the direction of the magnetic field. So the magnetic field is out of the plane of the blackboard, goes in here. Okay, if I get closer to the wire, I can draw these smaller circles. Okay, but at closer distances the field is higher. Okay, so if I draw a cross section of the wire, if I look at this wire from the end, suppose the current is coming out, my magnetic field lines, which are now connections of the magnetic field vectors, they are concentric circles. So the current is coming out, the magnetic field is a circle that is centered at the location of this wire. Okay, closer to this current carrying conductor, the field lines are closer together because the field is higher. Okay, so I will draw these lines with a higher density closer to this. Okay, current is going in. Okay, the field lines then get further and further away, but they're still concentric with the current carrying conductor. Okay, so the field lines are spaced further apart because the field is dropping with 1 over the distance. Okay, alright, so far so good. Now suppose I have a current carrying conductor. The current carrying conductor is such that the current is coming out. Now I'm at a certain distance R1 from this current carrying conductor. Let me draw a better circle. Okay. Now what I would like to do, I would like to be at this point. The magnetic field at this point, of course, is tangent to the circle, isn't it? So if I draw the magnetic field at this point, the magnetic field is like this. Here the magnetic field is like this. Here it's like this. So at each point it's tangent to the circle. I'm so sorry. Okay, and this continuous pink line is just connecting the tails of these magnetic field vectors. So these are magnetic field lines and these are magnetic field vectors. Both of them represent magnetic fields. Alright, now the magnetic field here has the same magnitude as the magnetic field here because all of these points are concentric with the location of the current carrying conductor. Okay, now what I would like to do, I would like to take this formula which we've already derived, B, take the 2 pi r to the left hand side, I get B into 2 pi r, 2 pi r1 because my radius is now r1, I get mu naught times the current that is coming out of this wire. Okay. Now let's look at this relationship. B into 2 pi r1 is mu naught I. Now what I would like to do, I would like to take the same amount of current I, and now I would like to draw a bigger circle around it. Now the radius of this circle is R2. Now the same formula would apply, and I would get B at the location of this circle is going to be different. B into 2 pi R2 is now going to be equal to mu naught I. Okay? The field is different. The field is now mu naught I over 2 pi R2. So I take 2 pi R2 to the other side. I call this field B1. I call this field B2. Okay? Now this B2 field is pointing in the same direction, but it's smaller than the B1 field because we're further away from the location of the current carrying conductor. So this is the B2 field. These vectors are smaller than the vectors that I've drawn over there. But for each case, if I take the field along this path and multiply it by the circumference, the total length of the path, I get mu naught I. Correct? So this equals B1 into 2 pi R1. So I can draw a current carrying conductor. I can draw two concentric circles around this. This is my path number 1. This is my path number 2. I can find the magnetic field along this path, at each point along this path. Okay. Now since the magnetic field is pointing, it's tangential to this path, if I break up this path into small line segments, then my displacements are also tangential to the path. So these are my directions of B, and if I break up this path into small line segments, then each line segment is also along the tangent. So the DLs are also along the circumference of a circle. The net result is that the magnetic field and the small DLs are always parallel to one another. The angle between the B that locally exists at this point and the infinitesimal distance that I've moved is 0. Because the DL for a circle is also along the tangent. Hence, this B times 2 pi R is simply a dot product of the B, the local magnetic field, with a small increment in distance that I make, and I integrate over the closed path. Okay, so what I've done here is I've taken a circular path around this current carrying conductor. The magnetic field is tangential to the circle. The small distances that I move are also tangential to the circle. Okay, so this thing B into 2 pi R is simply the constant magnetic field along this circle multiplied by the total circumference. But I can break up the circumference into small segments. So what I do is I take the magnetic field locally at any point, take its dot product with the small amount of distance that I move in a certain direction. This is also tangent to the circle, this vector, and so is this. So I get B into DL, and when I integrate, this B can come out of the integral, and I'm left with B into the total length that I moved in the circle, which is just the circumference. So I get B dot DL, this equals mu naught I. No matter whether I take this circle, this inner circle, or the outer circle, I get the same left hand side and the same right hand side. In each case, the dot product of the magnetic field with the small line segments integrated over the entire path gives you the same value of mu naught times I. So I can draw bigger and bigger circles, smaller circles, all enclosing this current. With the current at the center of the circle, I will get the same result. Another way to look at this is that if I am further away from the current carrying conductor, this B varies as 1 over R, it decreases. This circumference is proportional to R. So the total path length goes up. So if I move this along this path in the counterclockwise direction, I am parallel to the field. So if I move in the counterclockwise direction, I am parallel to the field, the angle between B and DL is always 0. So I take the local dot product between the magnetic field and the infinitesimal length that I move and integrate over a closed path, and I get mu naught I. This is called the Ampere's law. But this is just the simplest version of it, and it's incomplete. We'll complete it later, but this is a partial version of the Ampere's law. And let's compare it with Gauss's law. What Gauss's law states is that if I have an electric field E, I take its dot product with an infinitesimal area, the area of a small patch, and I integrate over the closed surface. The surface exists in 3 dimensions. This path exists in 2 dimensions. This is a path, a loop. It's not a surface. It's just this trajectory. Okay? Whereas in the Gauss's law, we integrate over a closed surface. Okay? So the Gauss's law would give us this integral. So you take the local electric field, the local area vector at each point in the volume, take the dot product and integrate over the surface that exists in the volume. What do you get? 1 over epsilon naught into the charge enclosed. Okay, so evidently there is a reciprocal relationship between epsilon naught and mu naught. What the role that the static charge plays in the electric field, in electricity, is played by a moving charge or a current in the magnetic field. This is the current enclosed. Now let's look at more examples of the Ampere's law. Suppose I have the same current carrying conductor. I choose a path like this. Okay. Now this is a closed path. For application of the Ampere's law, I need to have a closed path. It's a closed path, right? Does it enclose any current? No, it does not. Let's see if the Ampere's law works. Because in the Ampere's law, you have to have a current that passes through the loop. So if this is our loop, and we suppose that there's a rubber membrane that is inside the loop, and the loop is on the perimeter of this rubber membrane, does the current pierce through this membrane or not? No, it doesn't. So it does not enclose any current. Let's see if Ampere's law works here. So let's suppose this distance is R1, this distance is R2, right? The distance from the current carrying conductor. This angle is theta. Let's call this point 1, 2, 3, 4. Okay? Now if I go from 1 to 2, B dotted with DL going from 1 to 2, okay, plus B dotted with DL going from 2 to 3, plus B dotted with DL going from 3 to 4, okay, plus B dotted with DL going back from 4 to 1, so that we make a closed loop. This is the left hand side, okay? So I break the total path into segments. This is a natural fragmentation that I can do. Okay? Let's see what this integral turns out to be. So I'm taking the magnetic field at each point, taking its dot product with the infinitesimal length vector at each point, and then integrating over the path. Now, what is this integral equal to? आप बताओ, पूछा आप साथ में से पूछ लें क्या पूछा है? ये इंटेग्रल किस चीज के बराबर होगा? From 2 to 3, what is this integral equal to? क्या बात हुई? What is this integral asking you to compute? It's asking you to compute the magnetic field dot product with the infinitesimal length vector. आप बताएं? जी from 2 to 3 आप बताओ जी खाली बी कैसे होगा? इर्तजा सोहेल आप बताएं। म्यू नॉट, अब भूल रहे, राइट हैंड साइड को भूल जाओ एक वक्त के लिए। यू आर गोइंग फ्रॉम पार्ट 2 to 3. What is the mutual angle between the small distances you move and the magnetic field at each of these points? 90 degrees. So what's the dot product equal to along this path? 0. So this term goes to 0. This term goes to 0. Because along this path, the magnetic field is pointing like this. Along the tangent, right? Here it's also pointing like this. All along the path. Okay, it's circular. And the distance that you're traversing is along the radius. Okay, so the dot product, each of these dot products is 0, their integral must also be 0. So these terms are 0. Now we have to look at the first term and the third term. If we look at the first term, what is B? B is simply given by mu naught I over 2 pi R1. Okay? So along this path, the magnetic field is pointing in this direction, right? It's along the tangent. Okay? So, and its magnitude is mu naught I over 2 pi R1, because at a distance of R1, this is what the magnetic field is. And dl is, it has some magnitude dl. Okay? This is constant along this path. This magnetic field is constant along this path because it's at a constant distance from the current carrying conductor. And what's the angle between the length vector and the magnetic field? 0 or 180 degrees. It's 180 because the magnetic field is pointing in this direction and you're moving from 1 to 2. So you get a minus sign here. Okay? And you have to integrate from 1 to 2. ये समझ आई बात? ठीक है? इसी तरह यहाँ पे from 3 to 4, what's the magnetic field? The magnetic field is pointing in this direction along the tangent. Okay, and the magnetic field has to be mu naught I 2 pi R2 because you have the distance R2 from the current carrying conductor. And then you have dl. Now what's the angle between the small dl's and the magnetic field? 0. So cosine of 0 is 1. So you get a plus sign. And you go from 3 to 4. Okay? So I get minus mu naught I 2 pi R1. This is the total length of this segment, which is simply R1 theta. And what is this? This comes out to be mu naught I 2 pi R2. What is this length equal to? R2 theta. And I get 0. So I take this closed path, this special geometrical closed path in which this side is along a circle, it's an arc of a circle, this side is also an arc of a circle, and these are along the radius of a circle. I take a specially designed path and I find out that if I go around the path, so I'm going around a path, okay, at each point I am feeling a magnetic field. I take the dot product of the magnetic field at this point with the small distance that I move, distance vector. I go to the next point, I find out the field here, take the dot product with the infinitesimal distance that I move. Once again, I move all around the path in a counterclockwise fashion, and then I add up all the contributions between the magnetic field's dot product with the local vectors that I've moved. I get 0. Because inside my path, I do not see any current. There's no current that is piercing this path. So Ampere's law applies and I get 0. But that does not mean that the magnetic field here is 0. It doesn't mean that the magnetic field here is 0. It doesn't mean that the magnetic field here is 0. It just means that the dot product of the magnetic field along this loop is 0. Because it does not enclose any surface. Okay? If I have a charge Q, okay, and I draw any Gaussian surface that does not enclose this charge, what is the flux of this surface? 0. E dot dA on this surface is 0. But does that mean that the electric field here is 0? No, it doesn't mean that the electric field here is 0. There will be non-zero electric field everywhere. Exactly in the same fashion, when we talk about magnetism, we take enclosed paths, loops, and we're integrating the magnetic field over the loop, and it will give us the current that encloses this loop. Now let's draw more complicated paths. Let me draw a path like this. Now I draw this path. Once again, these are arcs of a circle, and these are radial. Okay. Now this path is a closed path. So for Ampere's law to apply, one has to have a closed path. And there's no current that pierces this path. If this path is on the boundary of some surface, okay, there is no current coming in or out of this surface. Okay, so the dot product of the B with dl along this path has to be 0 because it does not enclose any current. Now what we've drawn so far are nice geometrical paths whose sides are either along the radius or they are along an arc of a circle with the current carrying conductor at the center of the circle. But can we relax this condition a little bit? Let's see. We've actually proceeded when we were discussing the Gauss's law in the same fashion. We draw circular paths around point charges and then we deformed the surfaces a little bit. Okay? We had circular surfaces and then we made weird pear-shaped looking surfaces. Okay? Now we're going to use the same approach here and see if Ampere's law still holds. Alright. I have a current carrying conductor. I draw a path around it, circular path, and then I draw another path around it, which is not circular. Okay? This is at a distance r1. Now let's look at this region. Here, if I draw a chord, a segment, this angle is theta. Okay. Now along this path, I know that the magnetic field is pointing in this direction, and the paths are also parallel to the magnetic field. Okay, so if the field here is B1, okay, this path length, suppose it's some dl. Okay, suppose this arc length is dl. Then the dot product here is going to be B1 into dl, because the angle between the B vector and the dl is 0. Alright? Now if I have extended these lines so that they intersect the outer path. Now if I look at this outer path, the magnetic field here, what is the direction of the magnetic field at this point? It's tangent to this point? No, it's not. I can draw a circle that has this point as the center and passes through this point. The magnetic field is going to be tangent to this circle that I draw. Okay, because the magnetic field is circular. Correct? So the magnetic field lines are circular around this, with this as the origin. The path does not change the magnetic field. The magnetic field is tangent to a hypothetical circle that we draw. However, the infinitesimal distance that we move is tangent to this curve. So if this is the direction of B2 at this point, then the direction of the infinitesimal distance that we moved is along the tangent to the blue curve at this point. Okay? Do you agree with me on that? Now what is this angle? Theta. Similar triangles once again. So if I take the dot product of V2 with the dl, is simply B2 dl. This is dl1, this dl1, I call this dl2, dl2 cosine of theta. Okay, so this is B1 into dl1, this is B2 into dl2 cosine of theta. Okay, now what is dl2 cosine theta? dl2 cosine theta is simply this arc length. This is the length of the arc on this hypothetical circle that I draw, if dl is really small. Okay, so this is the arc length out on the outer circle, this green circle that I've drawn, this hypothetical circle that I've drawn. Okay, so this is the arc length on the outer circle, this is the arc length on the inner circle. B1 is proportional to 1 over r, this is proportional to r, this is proportional to 1 over r, this is proportional to r. So each of these will give you a constant, they will be equal, which is going to be equal to mu naught I. समझ आई बात की? नहीं समझ आई? यहां तक इस B1 डॉट dl की समझ आ गई? ठीक है, अब हमने ये देखना है, इसको मैं थोड़ा सा क्लोज अप करना चाहूँ यहां पे. This is a close up of this section. Okay, now this is my current carrying conductor. I'm looking at this point. At this point, the direction of magnetic field has to be determined. So I take this point as a center and I draw a circle. Okay, so the magnetic field will be tangent to this circle. Agreed? ये बात समझ आई? So this is B2. Okay, but I'm moving along this path. I'm not moving along the circular path. Okay, so my dl vector is tangent to the path. Okay, so this is dl2. ये बात समझ आई है या ये भी नहीं आई? समझ आई? नहीं? कुछ हाँ ना, ये दो ही चीजें हैं ना? आप बताओ आगे बैठे हो, हाँ जी आगे ही है ना, ठीक है। अब अगर सर्कल में मूव कर रहे हो तो B2 and DL2 are always parallel to one another because you're moving along a tangent and the field is also along a tangent to the circle. But now the field is tangent to a circle, but your path that you take is not a circle. It's a curved tortuous path. So your infinitesimal length vector is tangent to the path at that point. So this angle has to be theta. Okay, because these are similar triangles. This triangle that is formed here is a similar triangle to the triangle that is formed here. Now if this angle is theta and I am taking the dot product, so I am basically taking the product of B2's magnitude with DL2 multiplied by cosine theta. Okay, now let's look at this. I have a DL2. Okay, this is my circle, arc of my circle. This angle is theta. If DL2 is really small and I want to find DL2 cosine theta, then I can draw a right angle here. This length will be equal to DL2 cosine theta. I can do this, right? This is DL2, which is tangent to the path. This is my magnetic field, the direction of the magnetic field. I am taking the projection of DL2 on the magnetic field. This is what the dot product is. I can form this triangle locally at this point. This angle is theta, so the projection of DL2 parallel to the path is going to be DL2 cosine theta. But DL2 cosine theta, it's parallel to the magnetic field, so it's along the tangent to a circle. So this is just the arc of a circle. Since DL2 is really small, this arc matches up with this line segment, and this length becomes equal to DL2 cosine theta. So this right hand side is, if I integrate it later on, this DL2 cosine theta is simply, it's just going to be equal to B1 dl's integral. Okay, so at different points I can draw different circles. Here I am closer to the magnetic field. Here I am closer to the magnetic field. Here I am further away to the magnetic field. I take each of these paths along, I take each of these points along the path, form this local dot product. I will get the same result as I obtain from taking the dot product of the magnetic field along these points. Because if I am further away from the current carrying conductor, my B2 is small, but then my DL2 cosine theta is large. And they're larger by the same fraction. So if this is smaller by 1 over r, this is greater than 1 over r. So I take the local dot product, this result is independent of r. No matter I am close to the current carrying conductor or far away from the current carrying conductor, the integral is always going to be equal to mu naught times the current enclosed. Okay, this means that if I have a current carrying conductor and I draw a path like this, the integral will be equal to mu naught I. If I draw a path like this, the integral will still be equal to mu naught I. Okay, the integral of B dot dl along each of these paths is the same. I can draw any tortuous path that I like that encloses the current. Okay, I can have a situation like this. I draw this path. If I take the dot product of the magnetic field along this path and integrate over the path, what should I get? 0. I will still get 0, even though at these points the magnetic field is really high. Here I have, both of these paths are outside the magnetic field, outside the current carrying conductor, right? The current carrying conductor does not pierce this surface. So the total current enclosed is 0. And the point is that here the magnetic field is in the opposite direction as the magnetic field here, even though I am traversing this path in the same direction. So here the dot product is positive or negative, here the dot product is positive. So the positive and the negative contributions cancel out one another to give you 0. Likewise, if I have a path that is completely outside the current carrying conductor and does not circumambulate the current carrying conductor, उसके इर्द-गिर्द नहीं घूमता, the B dot dl's integral along this path will always be equal to 0. Okay? So B dot dl for this path is 0. If I have a situation like this, for example, I have a current carrying conductor which I am trying to draw in 3 dimensions. And this is the direction of my current. Okay? It's a loop. Now if I take a path, suppose I take this path. I would like to find B dot dl for this path. What is it going to be equal to? Mu naught I. If I deform my path slightly so that I have a path like this, this is my path. Okay. So what is B dot dl along this path? Mu naught I. What is I enclosed? Alright, now what I have here, if I look at this path from the top, what do I have? I draw this path, I'm looking at it from the top. So I have current coming out here, then I have current going in here, then I have current going out here. So this is my arrangement. I have 3 piercings. The current is going out twice and coming in once. Okay? This gives, if in this example, the current is going into the plane of the paper and my trajectory is in the same direction, B dot dl's integral will be minus mu naught I. Okay? If my trajectory is traversed in the same direction but my magnetic field is pointing in the opposite direction, I will get a minus sign. So outward coming currents give you a positive contribution, ingoing currents give you a negative contribution if I am traversing the loop in a counterclockwise direction. So I also have to identify what direction I am traversing the loop. So in this case I have 3 piercings, 2 coming out, 1 coming in. This contribution is plus I, this contribution is minus I, this is plus I. So if I take this path and find out B dot dl, it's going to be, its integral is just going to be mu naught I. Okay, if I drew my path in a different fashion, if this were my path, I would still get plus I. If I have twisted pair of cables, if I have a cable like this that is carrying current and then the current goes into a resistor and then the current flows back and it goes back into the power source, and I twist this cable, I can draw the twisting the other side of the cable like this, right? Okay, so this is my twisted pair of cables, commonly used twisted pair. Now I would like to take a path. Like this. Okay. If I traverse this path in any direction, what is the value of B dot dl? 0. because the positive going current is being cancelled out by a negative going current. The positive going current gives a positive contribution to P dot dl, the negative going current gives a negative contribution to P dot dl. So this integral is going to be 0. In this case, if these are really thin wires, will the magnetic field also be 0 outside? If these are really thin wires, we ignore the spatial dimensions of these wires. Is the magnetic field outside 0? Yes, it is 0. For this particular case, the magnetic field is also 0, because if you have positive going current and negative going current, the magnetic fields are totally opposing one another. So if you look at this arrangement from the top, you have a positive coming out current, the magnetic field going in current, the magnetic field is like this. And if I replace this with an outgoing current, the magnetic field is totally opposite to this in the opposite direction. So the magnetic fields cancel out. So there is no magnetic field outside the twisted pair cable. So B dot dl is also 0, the integral is 0, and so is B. This is a special case. In general, that's not going to be true all the times. Okay, so I give you half a minute just to relax a little bit while we move on after that. Alright, so let's look at some applications of Ampere's law. Remember, Ampere's law is one of Maxwell's 4 equations, but the way in which we've written it so far is incomplete. It's partially correct. There's another term which we'll learn later about, okay? And this can also compare with E dot dl. E dot dl's integral over a closed path is equal to 0 if we only have static charges. Okay? Now if I have a solenoid, you all know what a solenoid really is. It's just a loop of wire, a helical loop of wire. Okay? Suppose you have a long solenoid, ideally an infinitely long solenoid, and there is a problem in your tutorial which asks you to calculate the magnetic field for the solenoid. But the tasks are really simplified if we resort to the Ampere's law. Let's see how. Now current is flowing in the solenoid in a particular direction. If I look at the current carrying conductors from the front, at the top the current may be coming out, and at the bottom it may be going in. Okay? So I can draw a diagram like this. These are cross sections of the wire. Here the current is coming out, so I draw dots here, and here the current is going in. So I'm looking at the solenoid from the front. So current is winding around and whirling, going in, coming out, right? The current is moving forward. Okay, the charges are moving forward. And so on. Now I would like to find out the magnetic field inside the solenoid. Okay? And this is an infinitely long solenoid. So like Gauss's law, in Gauss's law we used to draw surfaces. We looked at the symmetry of the situation and draw a surface that conforms to the symmetry. Now we would like to draw a loop or a path that conforms to the symmetry. We make a qualitative guess of what the magnetic field will look like. The magnetic field inside the solenoid, if it's really long, is going to be parallel to the axis of the solenoid if this is really long, and outside the field is going to be 0. Why is the field going to be 0? Suppose you take some point here. The magnetic field due to this current carrying loop is pointing in this direction. The magnetic field due to this current carrying loop is pointing in the opposite direction. But this magnetic field of course is smaller than this magnetic field because this is further away. But if this is infinitely long and this is infinitely long too, all of these effects will totally cancel out to give you 0 magnetic field here. Okay? It's just like you have an infinite sheet of charge. Positively charged sheet, negatively charged sheet. What's the electric field outside? 0, provided the sheets are infinite in extents. Likewise, if this solenoid is infinite in extents, then the magnetic field outside will be perfectly 0. And the only magnetic field that can exist is inside the solenoid, and it has to be along the axis because that's the only non-unique direction. It cannot point like this, it cannot point like this, because all of these directions are totally equivalent for an infinite solenoid. So the only direction in which the magnetic field can point is along the axis. Okay? Now let's draw a path that conforms to these qualitative guesses that we've made. What kind of path can we draw? Circle? What kind of path? A cylinder. When I say path, it is not a surface, it's just a route. Surface नहीं बतानी, cylinder तो एक surface होता है. A rectangle. Let's draw a rectangle. Okay? Like this. This is a natural path that we can draw and that conforms to the magnetic fields that we've expected. These sides of the rectangle are perpendicular to the axis of the solenoid and these lateral sides are parallel to the axis of the solenoid. Okay? Now it does not matter if I draw this rectangle or I draw this rectangle. It does not really matter. Or I draw this rectangle. It does not really matter, as we'll see later. Okay? Now let's fix our attention on this rectangle that we've drawn. Suppose this length of this side is L. So this side will also be L. It's a rectangle. Now, we have to identify a direction in which we move around this path. So this is the direction. Okay? So we move counterclockwise. Now suppose this solenoid is constructed such that there are small n turns per unit length. Okay. Now we look at the Ampere's law. We have to form B dot dl along the path and take its integral. So we go from 1 to 2, 1, this is 0.2, 0.3, 0.4. Alright. Now if you look at the current carrying conductor, these current carrying coils are bringing current out of the plane of the paper. So the magnetic field will be parallel to this path along the axis, and the angle between these infinitesimal length vectors and the magnetic field will be 0. So the magnetic field which I can draw in green along this path is pointing in this direction. This is the magnetic field. So B dot dl along this path is positive. Suppose that field is unknown. So this is called B. And what's the length of this path? L. BL. So this is from 1 to 2. What is the dot product from 2 to 3? 0, because there is a field here in this region, but it's normal to the path. Outside there is no field. So the contribution from this side is 0, the contribution from this side is 0, and there is no field outside. Okay, so the contribution from this side is also 0. So the left hand side equals BL, and B is an unknown that we would like to find. Okay, now this must equal the total current enclosed times mu naught. Now what is the total current enclosed? Inside this path, how much current is piercing this surface that forms the inner surface of this outer boundary? Small n into I into L. Mu naught. So each of these coils carries a current I. How many coils do we have in this region? N into L. This is the number of turns per unit length, and the length is L. So what is my B? The L goes away, and my B is mu naught Ni. Ni is the total, and this is Ni, right? This is the magnetic field along the axis of a solenoid, inside the solenoid. We used Ampere's law to calculate it. देखो, from Gauss's law, starting from Gauss's law, we can calculate the electric field, provided there is some symmetry that we can make use of, that we can exploit. Here, from Ampere's law, we can calculate the magnetic field. So we can, from the magnetic field, we can calculate B dot dl integral, and we can also go the reverse. From knowledge of the Ampere's law, we are calculating the magnetic field. And why can we do that? Because there is a certain symmetry in this problem that we can exploit. Okay? Let's look at another example. Now we have a toroid. Now, if in this example of the solenoid, the magnetic field is independent of the length of the paths that I draw, provided the solenoid is infinitely long. It only depends upon the number of turns per unit length, and of course the current. Okay, more turns per unit length, higher will be the current. I can also have multi-layer solenoids. You remember the big solenoid that I showed you in class, along with the cathode ray tube? That solenoid has multiple layers. So if I have a multiple layer solenoid, current is coming out here. I can have another layer of coils. And all of these layers will contribute to the enclosed current. They will produce a magnetic field. Okay. Does this magnetic field depend upon how wide the solenoid is? It does not. Okay, bigger solenoids, if they're really infinitely long, will have the same magnetic field as thinner solenoids, if the solenoid is really infinitely long. So, the example of a toroid is a really important geometry because it is used in fusion reactors. In the tokamak, for example, in which you have to confine plasma so that it goes round and round and round in a circle. A toroid is just a hollow solid object in which the coils are wound around this solid frame in a helical fashion. So outside we have current coils that are bringing the current out, for example, and they are wound around this solid framework so that current is going in here, right? And this process is repeated all throughout the perimeter of this toroid. Now I would like to calculate the field inside this toroid. Okay, so I draw a path like this. The magnetic field, by symmetry we know, is going to point along the tangent, right? It's circular. So it's always going to be parallel to the path. And we traverse this path in the counterclockwise direction. So the traversal of this path is the same as the direction of the magnetic field. And there's no field inside, because there can't be, because of Ampere's law, and there's no field outside, because the current enclosed by a path that I draw outside is going to be zero. If I take this path, the total current enclosed is zero, because I have negative contribution and I have as many positive contributions. Okay, so the magnetic field is totally confined to within this region. Okay, this is how you can create a circular magnetic field pattern, and this is what is used in fusion reactors. Now if I would like to calculate B dot dl, suppose this radius is r of this path. Now I take B dot dl, suppose the magnetic field is B and dl are always parallel to one another. The circumference will be 2 pi r, and this will be equal to mu naught times the total current enclosed. Suppose there are capital N coils, okay? There are capital N turns. So I get mu naught N I. Okay? So my magnetic field will be B equals mu naught N over 2 pi R I. Okay? So now the magnetic field does depend upon the radius. You're closer to the inner wall, the magnetic field will be higher. You're further away, the magnetic field can be smaller. However, alright, so this is the magnetic field due to a toroid. G.
The number of turns will be smaller if the radius is smaller.
It could be multi-layer as well. This is a general relationship. It can vary from how you make the winding or not, but this is a totally general relationship. Okay, now let's look at a more interesting example. Okay, any questions up to this point? G. यहाँ पे इधर जी यहाँ पे कोई क्लोज पाथ बनाएं. The current enclosed is zero. The current enclosed is zero, so B dot dl will be zero. Okay, and fortuitously, by luck, the magnetic field is also zero. Okay, that's just by luck. If this distance is really large, if the radius of this toroid is large, provided the radius of the toroid is large, so that the distance of these coils from these coils is the same. So if this radius is large, then the field inside will be zero. Okay, now let's look at another example. Suppose I have an infinite sheet of current. Okay, अब इसको बड़े ध्यान से सुनना है. We have to go fast here. Now I have a sheet of a certain width. Let's call this width W. And it's infinite in expanse. ऊपर भी infinity को जा रही है, नीचे भी infinity को जा रही है. ठीक है, but I've only drawn a section of it. And it's carrying a current. Suppose that current is coming out of the sheet. Like this, okay? And it's a uniform current. It's coming out, okay? Suppose this current density is J, small j. Now what we would like to find out is the magnetic field due to the sheet of current. And we would like to use the Ampere's law once again. Now suppose there are two sides of this infinite sheet. I call this side 1 and I call this side 2. This is to the left of the sheet and this is to the right of the sheet. Suppose the magnetic field here is the Z component of the magnetic field here. Suppose it's called B1Z. Okay, its magnitude is B1Z. The Z component of the magnetic field. Suppose the Z component of the magnetic field is B2Z. Okay. Suppose these are the directions that I've drawn. Now let's make an Amperian path, like a Gaussian surface we call an Amperian path. Let's make an Amperian path which is rectangular, which conforms to the symmetry of the sheet, which means that it has two sides, one on side 1, one on side 2, and these sides are parallel to the sheet, and two sides along the width that are normal to the sheet. Okay, this is the Amperian path that we draw. Okay, suppose the length of this Amperian path is L, and it has some width as well, which is greater than W. Suppose we traverse this path in this counterclockwise fashion. Okay, now we would like to apply Ampere's law. Okay, now if this is the Z component of the magnetic field, the dot product of whatever magnetic field exists on this side with this length will just involve Z component. Correct? So the dot product on this side will be equal to, what will it be equal to? Remember, is the magnetic field different here from here from here? The magnetic field is going to be the same along a line that is parallel to the sheet, because it's an infinite sheet. So your here, this B1Z is not going to change. Okay. Now, what is the dot product of B1Z with DL along this path? It's minus B1Z into L. Okay? Agreed? Along this path, the dot product of B with L, but B can have other components as well. B can have a component like this, it can have a component like this as well. But for the time being, if this is the only source of magnetic field, there are no other sources of magnetic field in the entire universe, just this infinite sheet of charge. The magnetic field can only have a Z component. It cannot have an X component or a Y component, because this current is pointing out of the plane of the blackboard, so it can, and this is an infinite sheet of charge, so the magnetic field can only point along the Z direction. It cannot point along the X direction or the Y direction. Do you tend to agree with this? Because if I have two current carrying conductors, right? This is a current carrying conductor, this is a current carrying conductor. I draw the field due to this, it looks like this. I draw the field due to this, it looks like this. If I use the principle of superposition and I would like to draw the field due to both of these conductors carrying current at the same time, these fields are going to cancel out. So I will be left with the field like this. Okay. Now if instead of two conductors, I have really a large number of conductors close together, and this goes up to infinity, then the field can only point parallel to this sheet of current carrying conductor. So if I have an infinite sheet of charge, the only magnetic field that can exist is along the Z-axis, is parallel to the sheet. So the dot product of the magnetic field, whatever it is, it's only a Z component. With this path is 0. With this path the dot product is also 0. And here it's non-zero, and it's going to be B2ZL. Correct? So this is the left hand side of the Ampere's law. What is this equal? It's going to be mu naught times the the current enclosed. Now what's the current enclosed? कितना करंट है इसके अंदर? इस पाथ के अंदर से कितना करंट गुजर रहा है? इंफिनिटी नहीं।
एरिया के साथ
ये बताओ क्या है?
सर आई डॉट डी ए करेंगे और एल इंटू डब्ल्यू करेंगे।
J into L into W. J into L into W. Because this is the current enclosed. The current density is J. This area is L times W. So the L goes away. I'm left with B2Z minus B1Z equals mu naught J into width. जी मैंने अभी शुरू में सेम रखी है, मुझे पता नहीं है ना किस डायरेक्शन में है। मैंने कहा कि अगर ये डायरेक्शंस होंगी तो दिस इज द फॉर्मूला दैट नीड्स टू बी सेटिस्फाइड। लेटर ऑन विल फाइंड आउट व्हाट इज द रियल डायरेक्शन ऑफ द मैग्नेटिक फील्ड। ठीक है, ये बात समझ आ गई आपको? समझ आई? समझ आ गई सब? क्या इस साइड पे भी तो देखना है ना, B2Z is parallel to L. So I take the dot product B2Z with this L. I get plus B2Z into L. ठीक है? Alright. Now let's look at this object. J into W. आपको बहुत खूबसूरत रिजल्ट नजर आने लगा है, थोड़ा सा सब्र। देखो बड़ा जरूरी होता है कि अच्छी साइंस या अच्छी फिजिक्स पढ़ने के लिए आप हैरान भी हो। सरप्राइज इज द फर्स्ट स्टेप टुवर्ड्स एन अंडरस्टैंडिंग ऑफ साइंस। सो इन आवर फेसबुक एज वी जस्ट लॉस्ट होल्ड ऑफ दिस trait of surprise. We never surprised because we always have Google at our disposal, we always have Wikipedia, we have smartphones in our pockets, and we can always go back and think that we can go to Wikipedia and see what's going on. But without surprise we can't do any physics or science. So in this particular case, if you look at J times omega, this is current density, amperes per meter square into meters. So this dimensionally is amperes per meter. Okay, let's call this quantity J omega. Let's denote it by some capital J, by a strange looking J. Okay, and let's call it the sheet current density. Sheet current density. Okay, if I look at this, this is current per LW into W. This is current per unit length. So this is just how much current is passing through unit length of this sheet. Okay, so this sheet current density is a special quantity that we've defined, right? It tells you how much current is passing through unit length of this sheet. Current density is generally current per unit area. This is current per unit length. Okay, J omega is I, L omega into omega is I per unit length. So this is called the current sheet current density. So let's look at this formula. B2Z minus B1Z must equal mu naught times this J. Okay, अभी मैं ठीक है? All right. Now the question I would like to ask, if you look at the symmetry of this example and I ask you what should be the magnitude of B1Z as compared to the magnitude of B2Z, what should your answer be? They should be the same because it's an infinite sheet of charge and there is no difference between the left side from the right side. Okay, and there's really no difference, it's infinite, so I can move this path, I can make this path go like this. It go further away, the magnetic field does not change. So both of these magnitudes must be the same, and if I want to satisfy this equation, this magnitude has to be the same as this magnitude, and the difference of them is equal to this. So if I set this equal to mu naught J over 2, I can set this B1Z to minus mu naught J over 2, right? And then I take this difference, minus minus gives me plus mu naught J. So this is the only way in which I can satisfy this equation keeping this magnitude the same as this magnitude. But I need to put a minus sign with this B1Z. Okay, so this means that my B2Z is actually in the direction that I've drawn, and its magnitude is mu naught J over 2, and B1Z is minus mu naught J over 2, which means that the B1Z that I've actually drawn, the real magnetic field, is opposite to the direction that I've drawn. So the real magnetic field is pointing downwards, and its magnitude is minus mu naught J over 2. So if I draw the infinite sheet of charge again, the width of this sheet does not matter at all if it's infinite in size. The width does not matter at all. It's not appearing anywhere. So if I draw this infinite sheet of current that's bringing current out into your face, then the magnetic field on this side is going to point in the upward direction. Okay, and its magnitude is going to be mu naught J over 2, and the magnetic field here is going to point in the downward direction. And since I've drawn equally spaced lines, it means that the magnetic field is the same in this region of space, and it's the same in this region of space, and the magnetic field, however, is in the other direction. So this is minus mu naught J over 2. Now can you find any comparison with what we studied when we were studying Gauss's law or electricity? Is there any comparison that can be drawn? Capacitance, Kimi. Can you think of an analogy, which is the real really beautiful part? Sigma over? If I have a sheet of charge that carries a charge density sigma, okay, and the electric field here, which is normal to this sheet, I call this E1, and I call this electric field E2. Okay, then we know from Gauss's law that if I draw a Gaussian surface like this, okay, then I will have E1 A minus sign plus E2 A must equal 1 over epsilon naught sigma A. Okay, the A's will go away, and I will be left with E2 minus E1 is equal to sigma over epsilon naught. Okay, and if this is infinitely charged, for example, it's positively charged in an infinite sheet, then if I would have to satisfy this equation, the magnitude of E2 and E1 must be equal, and E1 must be pointing the opposite direction than what I've drawn. So if I have a positively charged sheet, the charge configuration, the real charge configuration looks like this. Agree? And there's a difference. Here the electric field is switching its direction. So the change in electric field is given by sigma over epsilon naught. Here the change in magnetic field is given by mu naught into the sheet density. So the exact analogy reveals once again in its pristine beauty. Mu naught is reciprocal to epsilon naught. This charge density is the same as the sheet current density. And the other point that you will notice, which is really important in the tutorials next week, is that the electric field here is taken to be normal to the surface. This is a normal component of the electric field. Here, the magnetic field is parallel to the sheet. Now suppose, please, just a couple of more minutes. If I have a region of space in which there is a uniform field that already exists, okay, a uniform field already exists, some B naught. Now I place my infinite sheet that is carrying a current out of the plane of the paper. Okay. What will the new magnetic field configuration look like? Now it's going to be superposition of this uniform field with this field. Okay? So what will I get as a result is the following field pattern. The field will go up to the right because here the field due to the infinite sheet of charge is parallel to the ambient field, to the field that already existed. So the field here is going to go up. The field lines will get closer. Here the ambient field that existed already is opposite to the field created by this infinite sheet of charge. So the field lines will get further apart, the field will go down. Okay, so this is the new magnetic field pattern. A field could have also already existed in an oblique direction. If this were my original field, okay, and I place my current carrying conductor inside this original field that is bringing current out, what will my new field pattern look like? So here the magnetic field is in the upward direction, so this will curve slightly up, okay, like this, and this will curve slightly down like this. Okay, depending upon the relative magnitudes of the ambient field versus this field. So the magnetic field need not be perpendicular to the surface. But if you apply the Ampere's law here, again, this rule is still going to apply. The Z component of the magnetic field along the two sides always follows this relationship. We'll look at more examples of this in our recitation on Monday. Next Friday is going to be a quiz, inshallah. Thank you very much.